This week's lab is all about working with and interfacing with memory, and specifically data memory. And a reason we have a whole lab dedicated to that is given the complexity of that memory component itself. One implementation detail we haven't really been talking about a lot, we haven't been doing any of in practice, it involves the understanding that all of what we were modeling using VHDL ultimately has to correspond to some underlying hardware implementation at the end of the day. We've been focusing on getting things to correctly simulate in ModelSim, which is a necessary first step. But as the complexity of the components that we're building with get more advanced, we tend to have to rely on specific tool supported implementation flows, as well as technology that targets our particular underlying piece of hardware. And for that reason, when working with things such as memory and memory, beyond just the size of the register file we've already built, we tend to have to follow a design methodology given to us by either the tool manufacturers, and this would be Cordis or Vivado versus ModelSim in this case, and also supporting the particular underlying platform. In our case, the DE2115 board that you've used in CPRE 281, and we will use again in this class in 381. And so for memory, what tends to be the case is as opposed to trying to design a memory from base principles, and we can, and we have in terms of that register file is a type of memory, we tend to need to follow a very particular implementation style. There's really two different approaches we can take. The first is we look at the documentation that says if you would like a memory using this tool for this particular FPGA, you must have code that looks like the following. And that's referred to as hardware inference, where if you write your code following a certain very specific design pattern, the tools are clever enough to determine that, oh, yes, this is some behavioral code. It's actually meant to correspond to a memory. We're going to take that block out and replace it with the resulting memory on our underlying FPGA. The other approach is referred to as designing with intellectual property cores or IP cores. Intellectual property is a legal term of art, but in our use case, it refers to pre-designed cores that tend to be customizable that are provided by either hardware manufacturers or tool support manufacturers and developers that allow you to sort of connect things together without having to write everything from scratch in our VHDL. Here I'm showing, this is a Vivado sample project that I've been working on. This is actually the starter design for CPRE 480. So if this doesn't intimidate you too much, you're going to be just fine next semester. It's got a lot of complexity going on. I'm not going into any of the details. This is a couple hundred hours of work getting this stuff to work so far. This is all based on an IP-based design flow in which all these blocks are added, sort of dragged and dropped, connected together via the GUI here. There's actually not a single line of VHDL or Verilog that has been custom written for this particular project, and there's still a ton of complexity there. So the IP-based design flow is not easier necessarily than a VHDL-based or Verilog-based design flow. It allows you probably to do more complex things because you're working with pre-existing components. But there's some complexity there. Since I didn't write any of these blocks, when any of these blocks doesn't behave the way I expect it to, I'm really back to the data sheet. I can't really go back necessarily. I don't even have access to go back to edit them to make them do what I want them to do. So the memory module that is provided for lab number 4 is also a type of IP block. It's a type that is auto-generated by Cordis tools, but it also allows the tools to then later infer that this was intended to be a memory block for your design. Looking at the code for it based on our understanding of behavioral VHDL, it's nothing too complicated, nothing beyond our skill set, I would certainly say at this point. We have a couple generics defined for a data width for a 32-bit memory. Address width is used to dictate how large the memory is going to need to be. And it's got ports that aren't all that different from our register file ports. It's a single write, single read port. So it has an address line, a data line for an input, and an output data line called Q, as well as a write enable port for it. And for this memory, it just defines as an internal signal, it defines in a type, an array of our standard logic vectors effectively, as well as then a single signal that's going to hold, in this case, with the default value of 10, 2 to the 10 words of memory in our data memory. And then the actual behavioral process isn't so different from one way you could have implemented your register file. Just a lookup into that array, returning that value back, or writing that value if the write enable is set to 1. So when we go to simulate it, it's pretty similar to simulating any other module. The one gotcha, and this is listed in the lab number 4 documentation, is there's a file here and it specifies a memory, but for this to be useful, it's nice to be able to pre-initialize that memory. That's what that attached dmem.hex file is doing here. There's a certain syntax that's supported directly by ModelSim that allows ModelSim to load contents into memory, and it's relatively straightforward. You can read through the documentation here. It assumes that things start at address 0 with some values. You can otherwise specify where you'd like other things to be located in memory, and it allows you to initialize the memory with the values that are in that file. But that does require, for this to work, we have to, every single time we want to get this design to load properly, we have to explicitly load the value back into our memory. The command is listed there in the Lab 4 documentation. It's mem-load. Grabbing this over here. This is the version that is listed in the design. So mem-load with an input file specifying, here's the actual dmem.hex file, -format hex. You have to be a little careful with these paths, right? We see these paths a lot when we're adding signals to our design, or when we get a number of warning messages associated with our design. We see these paths a lot. This path has to be, in this case, absolute and exactly corresponding to the module we're loading. This is assuming you had a test bench called test bench dmem, of which you had a port map labeled dmem, and then there's the underlying RAM component here. In this design, where I just loaded up that file directly, there is no test bench, there is no dmem, it's just called mem, and then that signal we're wanting to load into in the design is referred to as labeled as RAM. So that's why we're loading into that. So in the mem component, that RAM signal, load that file. And if we were to look at the actual signals here, one of them would correspond to that RAM. And in fact, you can actually go and see that all those values are listed there, all 2 to the 10, 1024 values. That is a pretty painful way to be able to debug what is in your memory, just so much you would have on your waveform. Fortunately, ModelSim does have this feature. If you go under View, and it's already selected here, but it's View Memory List, you can see all the different signals in your design that ModelSim is interpreting as being a memory. Basically, any really large signals, of which any of these memory blocks would correspond to a really large signal. And in fact, you can see it has a memory list. It mentions this component here. If you weren't sure what to load this as, it certainly does show up as here. And you can actually view the contents of that DMEM. And it's going to be a lot of junk. It's upper values to lower values here. But when we scroll all the way down, based on our hex file, the first 10 or so addresses were loaded, and then starting at address hex 15, you can actually see those memory values are there with the expected results there. That you can see it was just a set of values starting with 1 and incrementing up to 10. And then there's some additional values that start up at address 15 hex. That's address 21 in decimal here. So you're getting the values that you are expecting to see back. And then the nice thing about this is then you can run your simulation. You can be testing the things that you think you need to be able to test. And you can know at the end, did my memory actually get updated? Do I have the values I was expecting? Am I reading and writing from this as expected? That allows you to test your memory in isolation. That makes it a lot easier to test that your MIPS code that you're running at the end of lab number 4 is doing what you're expecting to do. So good luck with lab number 4. You have plenty of time to work on it. I know some of the time is going to be spent sort of fixing maybe some bugs that were showing up along the seams of lab number 2 and lab 3, and that's okay. That's part of the time baked into lab number 4. Let me know if you have any questions, as always, and good luck.